Here we go. So lesson 4.1, we went over the idea of how to turn simple interest into compound interest. And compound interest, we learned, could happen multiple times per year, not just yearly. So a review of those formulas. So the first thing is just a reminder about simple interest. So simple interest is pretty straightforward. You have some amount of money, we call that P. And simple interest is usually just given the letter I. So P is some starting amount, we call the principal. R is some rate, usually a yearly rate, and some amount of time goes by. So we have this P times R times T, often just written P, R, T. The lack of a symbol means multiply. I like to write those multiplies in. And once that simple interest is paid out, then if you put all that together, you have some future total, which is the amount you started with plus your interest. The interest is that PRT up here, so that gives me P plus PRT. So this just says, hey, this is what I invested, this is the interest they gave me, and it turns out we learned we can factor this formula and write it as P times 1 plus RT. And simple interest is just a single payout, boom, done. That's the end of it. Compound interest is when you take that money and you reinvest it in the same account. So we turned this into compound interest. And at first we just looked at basic yearly compound interest. And I'm not going to go through all the work we did to come up with this, but we came up with a formula that says for compound interest, the future amount looks kind of similar to simple interest. We get a P times parentheses. In the parentheses is just the 1 plus R, and the T pops out as an exponent. Okay? And this is an exponential equation. So a couple of super important formulas here. I'm just going to reiterate that simple interest is just some initial amount times a rate times a time. That's simple interest. We can put that together when we get the payout to get a final total value right there. So that's simple interest. When we switch to compound interest, where our interest gets put back in the account, our interest collects interest, the important thing here is that the T pops out as an exponent, and we end up with an exponential function. Whereas just straight simple interest, this up here is linear. So we took simple compound interest a bit farther by realizing, well, you could collect interest multiple times per year. So then we came up with this general compound interest formula. I'm just summarizing what we went over last time. And the big things from last time were the basic yearly compound interest and the general compound interest formula. And those are based on the simple interest stuff we played with at the end of module 3. So the general compound interest formula, we get a future amount is the present amount times this parentheses. In the parentheses is 1 plus our rate divided by this number we call n, and I'll re-explain n again, and we get this exponent n times t. And we're going to look at the calculator versions of these because you got to be careful using this on a calculator. Order of operations mattered. The big things here that were new compared to the basic yearly one is this n that I have. That's the number of periods per year that we get interest. And those numbers are either like just once a year, as this green formula up there, but n could be 1 for yearly, 4 for quarterly, 12 for monthly. We could even collect interest every day, 365 days in a year, among other options. But the common ones are yearly, quarterly, monthly, daily. Other important things to point out about this formula right here, the exponent is super important, the power. That's the n times t is the whole power up there. And that right there is the total number of times we collected interest, the total number of periods. Right, not just 1 year, but however many years went by, right? N is just how many times in 1 year. The power, nt, is the total number of times. So like if we were doing monthly, n is 12 times a year. But if 10 years went by, 10 times 12 would be 120 months passed, and our power would have to be 120. Okay, so that's super important. Other important thing is this r over n here. That's another important part of this formula. So r over n, this is the periodic interest rate. Periodic interest rate. Right, so for example, it could be a monthly rate. And we'll look at that in just a minute in a particular example. Usually R is an annual rate. Remember we had the idea of APR. That's what our R is. That means annual.
Can I ask you one quick thing?
Sure.
No, when you and I went over this, the only way it worked in my calculator is if I put the N and the T in parentheses also.
Yeah, so some calculators, and it depends on the calculators, the power has to go in parentheses because there's more than one thing happening up there. It's not just a single number. So if you're doing that multiplication up there, then it has to go in parentheses. If you did the multiplication ahead of time, then you just put the number there. Okay, but yeah, some calculators need that.
Okay, thank you.
All right, so let's just look at an example of this right here. So let's look at compound interest. Where we're going to invest $3,000 at an annual percentage rate, APR, of, let's go with 4.5%. Okay. So the investment, that's my P. The APR, that's my R. And then the other thing I'd have to say is how often do I collect interest? And let's do monthly compounding. So the problem might say, hey, we're compounding monthly, or it might just say you get interest every month. If you see the month in there, that means n is equal to 12. So if no other information is given, then I can start filling out the formula. So my formula is F equals P times parentheses 1 plus R over N, parentheses to the power NT, and sometimes the power needs parentheses, depending on your calculator. So in this case here, I get the future value is based on my current investment, my present investment of $3,000, times parentheses 1 plus 0.045, right, because percent means divide by 100, over that 12 months. And notice the 12 is only under the rate. It's not under the 1. So that's an order of operations issue that we may come across. And then the power here would be 12 times t, and that may need parentheses. So this is a formula for any number of years. If somebody says, hey, what's going to happen in 1 year or 10 years or 50 years, I just plug in how many years here. So T is always the number of years. So let's find the future amount. For 20 years later. Okay, so for that, I need a calculator or a spreadsheet. I'm going to just go to a calculator, and I'll try 2 different calculators to see how they work. I'm going to try my Google calculator, and I'm going to try my Desmos calculator. So first, the Google calculator. So I got my $3,000 to start with, times parentheses. And on most calculators, you don't need a times next to the parentheses. You can just have it, the parentheses there. And then it's going to be the 1 plus your interest rate converted to a decimal divided by the number of periods per year, in this case 12. So that's my base, close parentheses for the base. Then I got my power. So I raised to a power. Come on, Google. There we go. And in Google, I'm 90% sure I need the parentheses, but I'm going to try without and see what happens. So next I would type 12 times 20, and I noticed that the 12 looks like a power, but the 20 jumped out. So I realized, oh, oops, I guess Google needs parentheses here. So pay close attention to your calculator. So I need parentheses in my power, then 12 times 20. Okay, now I can see the 20 is in the power because it's higher and slightly smaller. So according to my Google calculator, I think the answer is $7,366, and I guess that would round to 40 cents. So I'm going to check that on my Desmos calculator, which is, Desmos is more like a handheld calculator. Google's like a phone calculator. So I need my 3,000. I like to put a times, but that's optional on most calculators. 1 plus my rate, 0.045 over 12. Now notice I didn't divide by 12 ahead of time to see what that was. I'm just typing exactly as the formula has it. And that's an important thing you need to try to do. Then I hit my power button here. And if I try to type the 12 times 20, let's see what happens. Notice that this calculator dropped the 20 out of the power. So that means this calculator also needs parentheses for the power. Every calculator is different. You just got to try and see what happens. And I got the same answer as the other one. The parentheses ensures the 12 times 20 is in the power, which is where it needs to be. Only the interest rate is divided by 12 here, not the 1. So please confirm that you can use your calculator to get the same value I did, $7,366, and then this would round to 40 cents. Questions on using that formula? Okay, so it's very important that you know what these formulas mean, what number goes where, and that you can use your calculator to plug it in. Something else to point out about this that's kind of cool. Chat. Okay, Texas Instruments calculator need the parentheses. All right, so that's good to know. I have one. Oh, I have a Casio. I don't know where I put my Casio. Must have left it at home. But my Casio one needs parentheses too. But again, it depends on the calculator. I have a friend that likes to use a TI called the TI-84, and I think that one doesn't need the parentheses. But again, you got to know your calculator. Interesting thing about this multiplication here is not only can this formula predict a future amount, but it can predict a past amount. And to do that, I just, on this side, notice it's a multiplication. So if I took this whole thing here, that I'm multiplying the present value by, and I divided it to the other side, then I can figure out, like, if I need $8,000 in the future, how much do I need to invest now? So it turns out I can reverse this for past amounts. And make predictions if you know what you want to have in the future. So to reverse that, I would get P equals, and then F would be divided by this crazy parentheses there. 1 plus R over N to the power NT. So for example, if I knew I wanted to have $7,366.40 in the future, 20 years later at 4.5%, I could then take that future number, plug it in, divide, and that would tell me how much to invest now. So I'm just going to check that to show it works. So this is just a cool twist on the formula if we solve for P. So if I start with $7,366.40, and instead of multiplying, I divide by that parentheses, 1 plus 0.045, oops, back over 12, raised to the power, parentheses, 12 times 20, I should see I get my $3,000 I started with back. So I can use that formula to take a present amount, predict what it's going to be worth in the future, or I could look and say, well, I want this future amount, how much should I invest now? So I can look, I can backwards predict with the formula too. It's kind of cool. All right, so next example, a comparison of simple interest and compound interest. So, new page. So these kinds of formulas don't just involve putting money in the bank. It can relate to other things too, like a new job. So my nephew just graduated from college and he's looking around for jobs and he gets this first job offer. And the first job offer is $40,000 per year. And there's a yearly raise. So at the end of each year, he gets a raise of 4%. So what would that mean? Well, in the first year, he's going to make $40,000. And then at the end of the first year, they calculate his raise. Now, we know about how compound interest works. So what that means is for the second year, he's going to, from that $40,000 base, we're going to multiply by 1 plus the rate of 4%. And 1 plus 4% is 1.04. And so if we make that calculation there to figure out what he's going to make for the second year, 40, 1, 2, 3 for 1,000 times 1.04. So I'm basically applying the yearly compound interest formula to his job, and it applies. So he's going to get a raise of $1,600 for the first year. So for the second year, he's going to make $41,600. And this idea, right, that's like our compound interest formula for 1 year. We have our starting amount times 1 plus R to the power T. And here I just let T be the first power, which doesn't really do anything. So if like he wanted to see what's going to happen 10 years later, then he would just take his starting salary, $40,000, and multiply by 1.04. to the 10th power, and that's going to be how much he should make if this situation doesn't change, right? If it stays at a 4% raise. 4% every year for 10 years, this is the calculation, right? It's just like compound interest. Now, so that's his first job offer, but he applied for a bunch of jobs. So he gets this offer and he says, okay, I'll get back to you in a couple of days. I'm waiting here on a couple of other jobs. And this other company says, hey, we want to hire you too. What's that other job offer you get? And this second job offer, they look at this job offer and they say, okay, we can beat that. Second job offer, they say, we'll also start you at $40,000 for your yearly salary, which says, okay, that's a match, that's all right. But we'll give you a yearly raise of $2,000. And he's pretty good at math. He knows, well, in the first year on the other job, they're only giving me an extra $1,600. These guys are going to give me $2,000. Now the catch here, it's exactly $2,000 per year. Right. So whereas in the other job, his raises collect more raises. Here he's just getting $2,000 per year every year. So is it going to be a better deal over the long run, or will the percent raise be a better deal, right? So this one here is a fixed raise. This one right here is a percent raise. And at first glance, this one looks like a better deal. He's like, oh man, that's more money than the other one. So if I just put this into a spreadsheet for a second to see what's going on, we've got two job offers. We've got one with the fixed raise. Let's do the percent raise first. We got the percent raise because that one came first, 4%. Versus the fixed raise at $2,000. I need a column for the years. Slide that over. So in the first year, either job, he makes $40,000. And then if we look at like second, third, fourth, fifth year later, the 4% raise is always going to take the amount above and multiply by 1.04. And the other job is always going to take the number above, but add 2,000, right? So that's a linear raise, the fixed raise. So then I only care about these two formulas right here, and I just want to fill them down and see what's going to happen. Okay, and let's clean them up for dollars and cents. So let's see. So the first year they're the same, second year the fixed raise is better, third year the fixed raise is better, fourth year the fixed raise is better, fifth year the fixed raise is better. So he's looking at this like, oh, I guess I should take the job, but they always gives me $2,000. But then a friend of his says, aren't percents better though? And he says, well, that percent's just less than 2,000. But if we expand this out a little bit to see if that's really true, what we're going to see is that eventually, where does it happen? Right here. In the 13th year, the other job is finally a better deal, right? So if I look at the difference here, right, if I take the fixed raise minus the percent raise, at first they're the same. And then if I copy that difference down, the fixed raise seems like, man, it's just a better deal for a long time. But then all of a sudden, the percent raise starts catching up. And between the 12th and the 13th year, the fixed raise stops being a better deal. And all of a sudden, the percent raise is a better deal. So if he's going to stay at this job for like 20, 30 years, right, 20 years later, the percent raise is a way better deal. 30 years later, it's a way, way better deal. So the point here is straight line raise versus percent raise. Ultimately, the percent raise is going to overtake the fixed one. It just might take a while. So it could happen sooner, it could happen later. But it's kind of an interesting comparison. And there's a homework problem and a lesson problem and an end of the week problem that are all just like this right here. All right, let's jump into the lesson.